Again, my name is Troy Leiser. I'm the Technical Director at Provectus Environmental Products. My presentation today is on our Provect-EBR system, quantum advancement in ISCO technology. Quick outline of the presentation. I'll do a brief introduction on Provectus as a company, go over our problem statement, ISCO, ISCR, and biotechnologies, why we use them, and then focus specifically on ISCO, how it works, and then briefly discuss the limitations of that approach, that technology, that chemistry, and then discuss the new technology that Provectus is bringing in, our Provect-EBR, and discuss some projects that we have with the EBR technology. A little background on Provectus. We've participated in well over 1,500 remediation projects with the personnel we have on staff. Our backgrounds are consulting, contracting, as well as product development and advanced technologies. Unlike the 100+ years that Keros has been in existence, Provectus is relatively new. We were formed in May of 2014 through acquisitions of well-established but not very well-used patents on ISCR, ISCO, as well as methane inhibition. We are a technology provider. If you have a site that requires turnkey type design, we have partnerships with industry leaders throughout the U.S. and other parts of the world where we can develop a turnkey site present if that's what you need. Otherwise, we basically are merely a technology provider. The chemistries and the new EBR that we're going to discuss today. Here's just a quick outline of various technologies. The one thing that I like with the approach that Provectus does is really knowing and understanding the site characteristics and applying the proper technology based on how the site is currently set up. We're not trying to fight against nature, but more work with it. So that kind of outlines some various technologies that we have in different site conditions in which we would utilize those technologies. So I mean, if you look at ISCO, ISCR, and bio, as well as our EBR, why those technologies are important in the market. If you look at the technologies that predated that, more of the pump and treat hydraulic control type technologies, those were very slow. They were, required significant investments in time. If you think of pump and treat systems, those can run for years and decades. Efficacy is always an issue with those. As they diminish in efficacy over time, can we reach our remedial objectives? Can we get down MCL levels? And then, obviously, a lot of things come down to cost. That high O&M, trying to maintain and operate those systems over longer periods of time. So a lot of those necessitate, bringing in the ISCO and ISCR type technologies. Just a real quick, brief explanation of ISCO. That's an operation where we're removing or pulling electrons from our contaminants. So we need something that can accept that electron. That would be our oxidant. And then the contrary is true of ISCR. We're looking to add electrons, so we need an electron donor to add electron to our contaminant. Just briefly describing those operations. So looking at limitations that we see in implementation of in situ chemical oxidation, looking at as Darren just discussed in detail, application of permanganate as an oxidant, and he touched on the non-beneficial consumption, that mass of your chemical that's being consumed by breaking down and interacting with things that you're not concerned about, and not going directly after your specific contaminants. If you look at some of the activation oxidants, a lot of times you have to use extreme activators, generating pHs of up over 10.5 or 12, or having to apply significant amounts of heat through thermal to generate activation. Those are all costly and time consuming, and sometimes hazardous to physically deal with. Longevity is an issue. Again, Darren touched on it with permanganate. that's a salt solution, so it's pretty much infinitely stable in the subsurface. But if you look at activated products, they're how long they're going to last in the subsurface once activated is greatly limited. And then you either need to, bring in additional chemistries to reactivate them, or just move on to a different technology. All of these factors lead to, what we consider contaminant rebound or desorption. And anybody that's been involved in these projects has seen it. Your first round of sampling, it looks great. We come back 3 months after that first round of sampling, and we start seeing that rebound, back to the same levels before we even started. So that's, creates issues with our clients, our regulators, our responsible parties, having to remob and bring in additional costs to try to get success at our sites. So all that, this is why this specific technology that we're bringing to market is important. That sign on top, that's actually a business here local to me. That's the kind of an older model bulldozer that they have up on a stand outside of their business. And like it says, you can't do today's job with yesterday's equipment if you want to be in business tomorrow. If you look at those photos on the bottom, your typical, I'm sure a lot of us have seen these injection rigs and injection trailers, mixing in chemical systems. That's our technology of yesterday. So we want to do things better and smarter. So why do we need a new technology to kind of replace that? Longevity, obviously. We want to be able to get those really reactive chemical species, those radical reactive oxygen species in the subsurface, but have them last for more than just partial seconds, which we see with the half-lives of a lot of these. We want to be able to set up PRBs with an ISCO type chemistry. You've seen some Keris used to do the candles or cylinders. Even the potassium persulfate is being, with its limited solubility, its potential for a PRB, but their uses and applications are limited. We want to be able to go after contaminants, that are recalcitrant to other technologies, be able to target deep aquifers or difficult lithologies that are challenging for normal application methods. So all that, all those factors bring us to bringing this specific technology to be able to address those. And that's the Provect-EBR or our Electro Remediation technology. In a, my elevator pitch, my quick description of it is, this system allows us to continually generate the most reactive of chemical species in the subsurface without having to manufacture, package, transport, store, or inject a single ounce or pound of any chemical. We are generating those reactive oxygen species subsurface on a continuous basis, and not having to be on site to do so. One of the really cool things about the system is it's computer controlled and monitored. You can see in the photo in the upper right, that's a snapshot of kind of a dashboard system that we're partnering with Field Data Solutions, and you'll hear from Mitch later on various things that Field Data does. But one of the things, they're active with us on this technology to be able to provide this dashboard so you can see the system operating really from anywhere on the globe. You don't have to be on site to do it. The photo on the right on the bottom shows the two downwell components of the system. In the foreground, you see the EBR reactor, and in the background, you see the sacrificial iron electrode. And the photo on the left shows the part of the inside of the control panel that monitors and maintains the system's operation. This is a patented technology by the Agresi Group out of Israel. We've partnered with the Agresi Group, and Provectus has exclusive license to this technology in North America, several countries in Europe, as well as Australia and Southeast Asia. This is patented both in Europe as well as here in the United States. So what, again, what this technology does is allows us to produce those Fenton type, reactive oxygen species that allows us to do, potentially that PRB for deep aquifers, tough, difficult lithologies, situations where, that sorption or sequestration or use of carbon merely to inhibit contaminant flux is not a good approach. And it's an alternate to those, high cost hydraulic containment pump and treat systems that we discussed earlier. Technology is applicable to a wide contaminant concentration range, part per million down to the sub part per billion level. How this system works, what we're doing, again, we are generating these reactive oxygen species. The electrode and the reactor are both in placement in a 4-inch PVC permanent well in groundwater, so they are continually in a groundwater atmosphere. The EBR reactor, through electrolytic reduction, takes that groundwater and converts it to molecular oxygen. And then on the cathode surface of the reactor, we convert that elemental oxygen to hydrogen peroxide. That hydrogen peroxide is continually in presence of ferrous iron that's released from the sacrificial iron electrode. And if you're familiar with, Fenton's type chemistry, hydrogen peroxide and the ferrous iron yields and generates those hydroperoxyl and superoxide ion, as well as the hydroxyl radicals, potentially ferrates as well. You see, sort of the reactions that are generated there on the lower right. That photo on the upper right is actually the EBR reactor inside of a tank of water that's actually running. You kind of see the effervescence, the bubbles coming up from it. That is the generation of oxygen and the conversion over to hydrogen peroxide. Those propagation reactions are really what drive how this system works. So we've got excess hydrogen peroxide concentrations that are used to drive these chain propagation reactions that continually produce those reactive oxygen species. The hydroperoxide anion, that acts as a strong nucleophile that's capable of attacking bonds of organic contaminants that are electron deficient functional groups. The superoxide anion radical, that will act as a weak nucleophile and a reductant, which is capable of destroying highly persistent compounds that are recalcitrant toward the hydroxyl radicals, such as hydrochloroethane and carbon tet. Additionally, that excess hydrogen peroxide then cycles a valence state of the iron from iron 2 to iron 3. It's that Haber-Weiss reaction where it shuttles that electron from iron 2 to iron 3, which continually presents that material required to generate these, reactive oxygen species. So we're able to generate that in an outward pattern from the EBR reactor. If you're familiar with electrofentons, typically an electrofentons generator can produce those radical species, but only right in direct contact with an EF reactor. The difference here with the EBR technology, we're generating these iron 2, iron 3 nanocluster particles that propagate outward in these low Fermi wave fronts. As you get those generation from that sacrificial iron electrode, you develop an equilibration of electron differentials, and that's what forces an outward migration of these particles to generate typically about a 15 to 20 foot ROI from each of the reactors. And we're actually able to generate a dynamic coupling from one reactor to the next. So it forms kind of like an interlaced mesh network from reactor to reactor to allow us to treat contaminants over a greater distance than what like an EF reactor would do. You know, again, at the bottom, the photo on the bottom kind of shows graphically that electro potential that you set up between the iron 2, iron 3 as it shuttles that electron back and forth. And with the ORPs that we're able to generate here, you know, as it states, you know, at ORPs of 850 millivolts, those electrons, you know, just kind of freely transfer back and forth from iron 2 to iron 3. It just shuttles that electron along and reinitiates those reactions to generate the reactive oxygen species that make this technology so effective. You know, again, just a quick summation of the technology. Again, we're able to generate hydrogen peroxide, the ferrous iron, to yield those radicals, you know, reactive oxygen species. In the photo in the lower right, what you see is a permanent placement of the EBR control panel at an active fueling station. And the photo on the left is actually a mobile system that we've set up here in the US that we would be able to either move around a site or be able to take it to different locations. Couple case studies I want to go over real quickly in the 4 or 5 minutes that I have remaining. This case study I like to present to show how the system is effective, kind of both up gradient and down gradient. This is a single EBR deployment. If you see in the photo or the schematic on the lower left, the EBR was deployed in wells that's marked W6A. We have 2 monitoring wells, down gradient 6B and W7, and also a monitoring well up gradient in W6. This was a chlorinated site with pretty high TCE concentrations. We're at 25 ppm of TCE, which is, you know, fairly significant concentration. The reactors, the electrode reactors, were deployed about 26 to 30 meters below ground surface. What we can show is from start point to 60 days, so it's a pretty short period of time. Not only well 6, which was 10 meters up gradient, but the 2 down gradient wells where we would assume we would see effect in well 6B and 7, but we're seeing effect 10 meters up gradient as well. So you see the TCE, we start again, we were at about 25 part per million. And we're able to generate concentrations, you know, at or below 15 part per billion. Our down gradient wells pretty much complete elimination of our contaminants there. So we were able to see 99% removal within that 30 to 60 days, not only down gradient but up gradient as well. One of the other case studies here, this is our Nievzednik site. This was MTB and TPH hydrocarbons. The one thing I want to show here, this is the ORP slide, where you see that once we turn the system on, we go from a slightly reducing to a strongly oxidizing condition within about a 2-month time period, and able to maintain that over extended period of time. This is our data sets, showing our contaminant elimination. But the one thing I want to show is the system here. This is our mobile system we've designed for here in the US. This is capable of running 10 reactors, and it's in a mobile 16-foot trailer setup. We've deployed this now 1 week ago. This past Monday, we deployed this system to an active industrial location in the eastern US. With a historic landfill that are contaminants, SVOCs and VOCs that are heading toward a down gradient critical waterway receptor, and this system is replacing the hydraulic containment that they've had in place for about 12 years. So this is just some of the pictures of that system as it's deployed. You can see our EBR trailer and our deployment wells, as well as some of the photos of the inside. So we do have the system up. It is running. We will be collecting data here on a continuous basis and be able to show that in our future presentations. Again, we're collecting information. The goal here is to be able to develop a predictive model that we can bring and show how it's going to be effective at other sites. We've got personnel across the U.S., not just myself. So again, if there's sites where you think this technology is applicable, please get in touch with us. Here's my contact information. I'll be back at the Q&A around 3 o'clock. If anyone has specific questions on how this technology works or may be applicable, drop a question in that question box, and we'll get that answered here at Q&A. And with that, I will conclude my presentation and turn it over to Bud Ivy.